Hi everyone. I just checking that. Yep, you can see my slides. Yep. So today I'm going to talk about quantifying variable importance. So basically, this is motivated by a lot of people who've come to see me where you've done a regression. And then after the regression, you look at your various predictor variables that you're using to try to predict your response. And you're asking which one's more important, which one matters more. So there's no universal definition of variable importance, and there isn't really a consensus on the best way. So it basically depends on what you mean by importance. So this should be driven by your study aims. So I'm going to talk through a few of the broad ways that people do define variable importance, and I'm going to focus on the concepts because it can be implemented in so many different ways. But I will also show you how to do it in R. So I just took this data set from Kaggle. It's a house prices data set to motivate the problem. So it's looking at, in this data set, you've got sale price of houses. They're obviously not in Sydney, as you can see how many zeros they have. And then there's three predictor variables: the lot area, the number of bedrooms, and the number of bathrooms. And here is just the output of a linear model where it uses these three predictors to try to estimate what the sale price of the house might be. So here's an example of what not to do. Don't use the p-values to think about variable importance. Here, if you're looking at what's more important, the number of bedrooms or the number of bathrooms, you can see that the bathroom variable was much more significant than bedrooms. What this means is that there's a bigger weight of evidence for the effect of bathrooms. It doesn't necessarily mean that bathroom has a bigger effect on house prices, or it's more important for explaining variation in house prices. Another thing that you should try not to do that is kind of common is to try to distinguish between highly correlated variables. So here's a quote from a famous statistician, Tukey, who said it's probably unwise to try to assign relative determinations to correlated variables. And this was in 1954, but it does remain true if two variables are very highly correlated, or a set of variables are very highly correlated. It's always going to be tricky and maybe spurious to assign one as having greater importance than another. You may just not be able to say that with the data set that you have. Let's go into what you can do. So just using this example, what's more important, house prices, bedrooms or bathrooms? And I did plot the bedrooms against bathrooms here, just check that they weren't too correlated. Just thinking about whether it's wise to distinguish between these two variables. There is an association between them, but I think it's okay to look into this question. So the first definition that you can use for for importance is looking at the unique variation in your response variable, so your y, that's explained by x. So the idea here is that you look at how much variation each variable uniquely explains that isn't explained by any combination of other variables. In this Venn diagram here, it represents the total variation in y that's explained by x1 and x2, and give x1 and x2 are somewhat correlated, and there's some variation that is explained by both of them, and then the shaded areas represent their unique contributions. So one thing you can do is to fit a model with both x1 and x2. Then you can remove x1 and then and compare how much the model deteriorates when you took out x1, and then you can remove x2 and compare and look at how much the model deteriorated when you took out x2. And so I'll talk about what you can use different metrics for model performance. For a linear model, like the house prices model, you can use the R-squared to look at how much the model dropped by, how much it deteriorated by when you took out each x variable. So you could define the importance as the R-squared of the full model minus the R-squared of the model without x. And so another way that you can do it for a linear model is to look at the root mean squared error of the model without x compared to the model with x. So that is just reversed because the error will go up when you take out x. So if x is important, we expect a big drop in the R-squared or a big increase in the root mean squared error. And just noting that R-squared and root mean squared error are just a scaled versions of each other. So it's just scaled by the total sum of squares for that sample. So we'll get the same answer. Just to go into this idea more, you can fit the model with all the covariates. So that's lot area, bedroom, bathroom, bedrooms and bathrooms, and then drop out bedrooms in the second line of code, drop out bathrooms in the third line of code, and then compare the R-squareds of those models. So the R-squared of the full model is 0.37. When you drop bedrooms, it goes down to 0.36. So the contribution of the bedroom variable is 0.01. And when you drop bathrooms, it went down to 0.299. So the contribution, the bathrooms variable was 0.07. Where are my slides? Going to the next. So now, and so you can do the same thing for root mean squared error. And now you've got of importance for the number of bedrooms and the number of bathrooms. And here you can conclude that the number of bathrooms is explaining more variation in house prices than the number of bedrooms. And so it's looking like about 7 times as much. So things to know about when the independent R-squared can be, so for the 3 predictors in the model, you exactly partition it into the contribution from bedrooms, bathrooms, what's that funny noise, and lot area. The variable I've got this
Hey Eve, Daniel Foster here. Your audio is dropping in and out, and so people are posting messages in the chat.
Okay, thanks. I might just have to very clearly and hope that my audio works. So yeah, not sure what I can do. So when variables are correlated, there is a solution. So variables are uncorrelated. Is it the video off to conserve? Okay. So how is this? How is the sound now? Better, much better. Great. Okay. You can still see my screen though. Yeah. So cool. So the I guess the only slide just moving on is that you shouldn't expect that those R-squared, like the contribution from each variable, are going to sum up to the total variation explained. But what it does give you is a measure of how much each variable uniquely contributes to the variation in Y. So another thing to know about the change in R-squared is that it depends on the sample. So it's R-squared is a function of the variation in Y and the variance of X. So when you get a different sample with a different range of Y values sampled, it can influence the R-squared. So if you sample a bigger range of Y values, you tend to get a bigger R-squared. But you shouldn't need to worry about this as long as you're making comparisons within a sample. So you're comparing the importance of two variables on the same sample. So it might not be, you need to be careful if you're going to make comparisons across different data sets. Another thing is that, with a linear model, you can also use other metrics, and root mean squared error is 1, and it's on the scale of the response variable, so it tells you how close your predictions are to actual values, and yes, you should just be guided by the information that you want to present. So that was the unique contribution that each X variable makes to Y, explaining the variation in Y as one importance definition. If you have a lot of variables, then you could run into a situation where the unique contribution of a particular variable might be small, but you kind of overall think that that's an important variable. So I just drew this funny diagram to try to illustrate this concept. So this is meant to represent the variation in Y explained by the model. And each circle, each color is like an X variable, and the size of the circle is representing like how much variation in Y is explained by a particular X variable. So if you take the green variable, it's explaining more variation on its own than any other variable explains on its own. But because the variables are all correlated, its unique contribution is actually not that much. So the shaded area represents its unique contribution that's not explained by any other variable. And this solid area here represents the variation explained by Y on its own. So, on its own, it seems to explain more than any other X variable. So one other definition that people have come up with is to look at the average variation explained by a variable. So here, what you do is that you fit regressions on all subsets of the predictors that you're comparing, and you look at the average change in model performance across models with that variable compared to the nested models within that don't have that variable via a method called hierarchical partitioning. So you use this method with different metrics to assess performance. And for a linear model, you can use R². So here I've written the equation. It's a little bit tricky, but you can see that there's the R² of the variable of the model with X minus the R² of the model without X. That's what this R² X H minus R² H is. And where H is representing all possible sets of the variables. So it is weighted by this K minus 1 choose I variable. That's just meaning that we're going to put more weight on the model that only has X in it. So we're going to compare the model that only has X to the model without X. We're going to give that a weight of 1. And we're going to compare the model that has all the variables in it to the model that has all the variables except X. And we'll also give that a weight of 1. And then we'll look at all the models in between, and they'll have slightly lower weights. So this is also related to dominance analysis, but I'm not going to talk too much about that. So it's a complicated formula, but how do you do it? There are packages that can do that for you, so you don't have to do that tricky coding yourself. So if we look at the average contribution of bedrooms versus the average contribution of bathrooms to house prices by fitting a model with all subsets of the predicted, fitting models with all subsets of the predictor variables. So here it's 8 models because there was only 3 predictors. Comparing the R²s, you can get the average contribution. So in R, there's a package called dominance analysis that does that hierarchical partitioning with R². And it can also do it for GLMs with other R² metrics. So it's just 2 lines of code. And the average contribution of bathrooms came out to be 0.139, and the average contribution of bedrooms came out to be 0.059. So one nice thing about this method is that these average contributions do sum up to the R² of the full model. And so ultimately, from a ranking perspective, the answer didn't change. We still find that bathrooms are more important than bedrooms for explaining variation in the house sale price. But the magnitude of the differences, the magnitude of these importance values is different. So now bathrooms are only roughly twice as important as bedrooms, whereas before they were 7 times as important. So you do get slightly different answers. And the third definition of importance that I'm going to go through is just looking at the effect on the response variable. So you might not need to use these variance partitioning methods. You might just be able to look at how much does a predictor change the response variable by. So regression, looking at your regression coefficient. So if the predictors are on different scales, you can scale them to have a mean of 0 and a standard deviation of 1. And then the regression coefficient will represent how much, if X changes by 1 standard deviation, how much does Y change by. But you don't have to scale the variables if you don't want to. Like sometimes there's a natural scale on which to compare your predictors and say which one's more important. So, you know, here I'm going to ask what impact does adding a bathroom versus a bedroom have on the sale of a price? And I don't think it makes sense to scale it. I think, you know, that people think about this question in units. So we're going to compare a 1 unit change in bedrooms to a 1 unit change in bathrooms and see which one's more important. The coefficient for bathrooms was 21,000, and the coefficients for bedrooms was like 4,700. So adding a bathroom seems to be more important, and it adds a lot more value to the house. So we've done these three broad methods, looking at the unique contribution, the average contribution, or the effect on your response variable. None of these ways are right. They all provide different information. And so before you embark on this kind of journey, you should be thinking about what you're hoping to find out and what your research aims are when you're asking what's more important. So it's all been linear models, but you can use the same concepts for more complicated models. So I really just wanted to focus on the concepts, and then you can kind of extend it with a bit more reading. If you move to a generalized linear model, you can't use R-squareds anymore, but we usually use deviance or pseudo R-squared kind of metrics in this context. So these are all based on the likelihood. So when you fitted a linear model, you used sum of squares to estimate the model parameters. When you fitted a GLM, you would have used the maximum likelihood to estimate your parameters, and so it makes sense to use likelihood-based metrics to rank the variables. So people like them to look like R-squareds. So there's a lot of pseudo R-squareds around. One of them is McFadden's R-squared, which is just 1 minus the likelihood with the variable over the likelihood, log likelihood without the variable. And another thing you also see them called is d-squareds, because they're based on deviance. So just show you an example of a paper that used this method, decrease in deviance explained. So this paper was looking at variation in landslide susceptibility. So it's a binary response. The sites either had a landslide or they didn't. And they compared a bunch of variables. They've had a bunch of variables in their model, and afterwards they wanted to look at how important they were. So here their model was actually a GAM. So they had wiggly terms through these X variables. So it didn't often, once your relationship between Y and X is nonlinear, looking at the regression coefficients becomes a bit harder. There's no direct comparison when you're not comparing one straight line to another straight line. So it does often make sense to go to an R-squared or a deviance explained kind of approach. So yeah, and so here in their setting, they found that the rainfall in the last 5 days explained the most variation in landslide susceptibility. And this is its unique contribution to the variation in landslide susceptibility. It can't be explained by other variables. So it also wasn't explained by the rainfall in the last 3 hours, for example. And forest type and the angle of the slope of the site were also quite important. So that's just somewhere where it's cropped up. And I just thought I'd give another example using the average contribution of predictors. So this is in a binomial logistic regression setting. So in this data set, which I got from the dominance analysis package, they were looking at the presence-absence of a tropical bird species and how it related to these 6 predictors. So remoteness, altitude, slope, rainfall, distance to the coast, I believe that is, and land. I'm not sure what land was. So using this data set, you can fit a GLM, a binomial GLM with all the variables. We're just going to assume that all the assumptions held and everything like that, and then use the dominance analysis package to look at the average contribution each variable made. So when you run this line of code, what it will actually do is fit 2 to the power of 6 different models. So it didn't take long, but it like definitely took more than instantaneously to fit to run this. And then it compares the models that had the variable to the models that didn't have it, and it used McFadden's R-squared. So it actually implements other metrics as well, but I believe that you'll get the same answer, just on different scales. So they in this study, remoteness came out as being substantially more important than any other variable for explaining the locations of birds. And I've got a reference for that package there. so what do you conclude? Remoteness is pretty important. Slope doesn't seem to be important. And distance to the coast is quite important, and there's not too much distinguishing some of these middle variables. So just a summary of the concepts that I've gone over that you can look for ways to quantify variable importance. There's the magnitude of the change in y when x changes, and you can use standardized or unstandardized regression coefficients, or model average regression coefficients is another option when you have a certainty that you've fitted the right model. So so people come at this question. Some people have a small number of predictors in their model, and that's when I would tend to use standardized or unstandardized regression coefficients, or look at the unique contribution of the x variable. When you have less certainty that you've ended up on the right model, and you're looking at variable importance, then it might make sense to look at the average contribution of x over a bunch of models, or model averaged regression coefficients, which I didn't really talk about. But that's basically fitting all subsets and estimating the regression coefficients in different models, and then averaging them with some weights. If you have a mixed model, you can use extensions of R-squareds for mixed models, like Nakagawa's R-squared. So there's some caveats that I just wanted to go into. These relative variable importance sort of ideas are for your finalized model. You shouldn't be using these for model selection. This is something that you've come to kind of almost as it could be like a post hoc question, like, oh, now I'm just interested in which one's explaining more. They are subject to the same issues as multiple regression. So if you try to distinguish between highly correlated variables, it could be quite unstable. And if you have a lot of predictors and not a lot of sample size, the relative importance measures are not going to be very accurate, and they're going to be very variable from one sample to the next. Your basic model assumptions still need to hold true. So I'm assuming that your model, your GLM or your linear model, has been checked, and you've done your independent, you've got your sampling design with independence, and your mean variance assumptions hold true, and that sort of thing. And the other thing is that if you took another sample from the population, it would produce a different set of importance values for each predictor. And they might be different relative to each other too. So there's uncertainty here, and you can estimate the uncertainty in these R-squared type metrics with bootstrapping. So the dominance analysis package does bootstrapping to estimate the uncertainty in average contribution. And regression coefficients generally come with their standard errors already. I'm sure you already knew that. And this is my last slide. I thought that I should say something about prediction, just because if your goal is prediction, the importance needs to be evaluated via cross-validation. So if your goal is to say which variable is more important for predicting y, then you should calculate the importance metric on independent holdout data. You can still use the same concepts as before, but you need to be holding out data you need to be splitting your sample into test and training to evaluate how well it can predict. And so random forests and other machine learning prediction techniques, which are designed to just predict Y, they have their own built-in importance metrics that come as a kind of a byproduct of the algorithm, and their importance metrics tell you which variables were important in determining the value of Y, and so it's slightly different to what I've been talking about here, but it's another definition of importance depending on if that's your aim, is to predict Y, then that might be a good way to go. So it was a tricky topic to research because I did find so many different things out there, but if you have any questions, I'll do my best to answer them. And so I'm looking in the questions window. When I use random forest, which metrics should I use to determine the importance of their predictor? Their p-value or their mean squared error percentage in the random forests? So I don't know that you traditionally get p-values from random forests. So generally, so generally you should never be using a p-value to determine the importance of a predictor. I'm not sure, I probably need to hear that question to interpret it, but any hypothesis test of whether is testing whether the predictor is statistically significant doesn't necessarily mean it has a big impact on your predictor. So you can have a variable that is highly statistically significant, but when you look at its coefficient, it's tiny. So a change in that predictor barely influences your response variable. So hopefully that helps. I'm happy to. So it would be looking at their mean squared error in the random forest. Is there a statistical test to test if the greater importance is statistically significant? Yeah, so that's a good question. So that's what I was trying to allude to at the end when I said there's uncertainty in the in these metrics. So because we don't generally know the distribution of these things, the approach that I've come across is via bootstrapping. So you bootstrap to figure out the uncertainty in the change in R squared. And so that, I don't know about a statistical test, but certainly you can put confidence intervals on, and that can give you an idea of whether this variable is really more important than another variable. Does that make sense? So, you know, one variable might be explaining 20% of the R squared, and another variable might be explaining 10%, but if the confidence intervals are really, really wide, that may not be statistically significant. And that might be because your sample size is quite small relative to the number of predictors, or because those predictors are quite correlated, so it's really hard to distinguish between them, and in different samples you get different answers. Nikki wants me to explain the hierarchical partitioning method a bit more. Share. I'll try to do one last quick explanation of it. So basically, if you had three variables, I'll call them x1, x2, and x3. You might fit the model with x1 and compare it. So this is the model with x1, and we compare it to the model with nothing. And then we fit the model with x1 and x2, and we compare it to the model with just x2. So we'll get a bunch. So I'll call this like the change in R squared here. We'll get another change in R squared here. And we'll fit the model with x1, x2, and x3. We look at all the possible ways x1 could be added to the model. And it could also be, I think there's one last way, just have x3. So these boxes are models. We can calculate the R squared for different models, and across these 4 different comparisons, we can average the change in R squared. It's a weighted average. So we can take a weighted average of these. That's the hierarchical partitioning, and so that will give us the contribution from x1. So it's kind of averaging. So this comparison here gives you the unique contribution of x1. This comparison here tells you how much x1 explained on its own without any other variable in the model, and then this tells you how much it explained if you only had x2, and this one tells you how much it explained if you only had x3. And so I guess the thing is, the unique contribution method, it does depend on what other variables are in the model, whereas this one will also depend on what other variables are in the model, but it can, if the variables are collinear, so if there's x1 is kind of related to x2 and x3, that as they were in the house prices data set, it can tell you, it just gives you a different answer. So it averages over its contribution in different models. So I guess when you have more uncertainty about what the model is, this hierarchical partitioning one sort of averages over that. Great. Glad that you understood. I didn't see if there were any other questions backwards, but it's probably just allow people to think of anything. What do you reckon, Peter? Are we...
I think if there's no more questions, then maybe we can call it a day.
Yeah.
So it doesn't seem like people have thought of anything else. If you've got a follow-up question, you can just send it to our email address if you're thinking of it while you're walking away, as sometimes happens. So thanks very much, Eve, for a really interesting and practical talk. There's a lot of stuff in there that people can actually go away and use, provided they stick to the caveats at the end.
Yeah.
Just a couple of announcements. The Thursday afternoon is also Hacky Hour afternoon. So if you've got any data questions that are not necessarily straight statistical, or even if they are, but more computing type questions, then log into Hacky Hour, because they'll be there till 4 o'clock. You can find the link on their webpage. And we'll be doing our last seminar for the year in November. The date and topic will be posted on our website in a week or two. So we hope to see you then. So thanks again for coming, and we'll see you next time.